Well, we ended yesterday with this statement and give one application to say that what are the maximal sets, but also it gives us the structure of Sumfree subsets of 1n or something like that, which are a cardinality which is less than m over 2, but not completely small. Good. And we want to prove that. You remember I was using in the statement I wrote yesterday, I was calling that m of capital A and this little m of capital A. We just take now the notation capital M, little m. If you have to use capital M, little m for a different set, then you'll see what it is. It's quite easy. Good. What about, yes, one point is about m over 2, and you have possibly to tune slightly what I am going to give in the proof, whether m is even or odd. You have to be a bit careful. I am not sure that something is absolutely perfect on what I'm going to say. In any case, you have to remember that if m over 2 is an integer, it cannot be in A, simply because m is in A, and A is Semfree. So maybe there are some little things to do. So we noticed indeed two things when we start the first point, which was to prove that the cardinality of a Semfree set in 1n is at most n over 2. We started with something which was, well, you know, when we have the sum of two elements in 1 and n, it is in the interval 1 and 2n. And this was not that pleasant. And we could say something that if the number of elements, first of all, couldn't be larger than 2n over 3, but this is much larger than n over 2. But at least if it was something like n over 3, we got something about the structure of it. Just by applying the 3k minus 3 or 3k minus 4, it depends how you want to pronounce it, theorem of Frerman. So this was one point. So this was good, but not that good. Indeed, in some way, you can prove n over 2 that way, but you have to produce a lot of energy for that. And it was not additive energy, but energy. But then, if you want to, we had this very simple proof that you have at most n over 2 element by considering also that it is difference-free. So it's nice also to introduce indeed the difference of A. We're looking at all the elements, simply the element which was capital N or capital M minus little a. And we're looking at this set. So this is what we are going to do, but instead of taking only capital N minus A, we want to take A minus A, the difference of all these sets. Now it means that if you want to look at the sum of such elements, then you have something which is different because you are summing two elements which are different. A and A minus A are different, or minus A simply are different elements. So you have to use something which is the sum of two different sets. And I think you mentioned this, or you proved maybe something about this adding different sets in a finite set in Z. In any case, I'll tell you what it is, what we use, which is from the Frerman of the very beginning of his study of those questions, that is to say, in the mid-50s. And he introduced something which he called, at that time it turns out, and in his paper it was Theorem X and Theorem XI, and I still call them Theorem X and Theorem XI. But we are in a special case because we are going to use elements which have the same number of elements and which are in an interval of the same length. So we're in some way in a special case, and I'm going to state this element in this context. Let me say how it goes. If you have two sets, before stating it formally, I tell you what it looks like. You have an interval of a certain length, and inside that, you have something which is, let us say, k elements. And you have another set in which you have k elements. So for me, K is equal to K. But it's not the same set. Here it is the same size. Fine. If it is not the same size, it works also, you can say something. Now the point is the following. If it is sufficiently rich, that is to say that if this is at most 2K, it's rather compact, then essentially you have something which would be considered in the 3K minus 3 Frerman theorem. You would consider that as being in some way an arithmetic progression or an interval with few elements, okay? And so when you are going to take this set plus this set, you will get something which is the size of which, the number of elements in it, is not only 2K. You can do better than that. It is the size here plus K. Okay? Of course, if this is completely compact and you have only a size K, well, okay. Then it is the 2K element and you have all the sets and you can do better. Now what happens if this is really much larger? This is very large compared to K. I mean, very large, slightly larger than 2K. If this is larger than 2K, you have something which is completely spread, because you assume always that this one is in the business and this one also. So it's not artificial that you say it is in a large set. Then you have something which is in a large set, and then you have something like that. Then you have at least 3K elements. Okay? Nothing to do with the size of that, because if it were not 3K, then you would use the 3K minus 3 Frerman theorem, and it will tell you that it has to be into something which is short. Okay? So this is in some way the philosophy. So you will have, I will now write them together, those two elements, those two theorems, and we'll write it like that. So it is a theorem, let us say, Frerman in the mid-50s, and what I'm looking at is special case. Okay. So it is the following. You take two sets. One set is S. So S is, well, you put 0. This is not a problem to put 0 because you can always shift your sum. If you shift the sum, you are just shifting, you shift your sets, you are shifting the sum, and this is not a problem. So you assume that 0 is in the business, less than blah, 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 less than Sm minus 1. Maybe I should have put K minus 1. The S is the K which is there. Okay, so this is the set of integer, and T will be the same thing. I mean, it's T0, less than blah, 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 less than, and of course, Tm minus 1. First of all, it is special case because Frerman can deal with the fact that this M is different from this one. Your set has not the same size, okay, not the same elements. Then you will have something which comes into the minimum of M and something like that. And for me, another special case is that this is exactly in the set, in the same sets. This is what you get, you see, when you take an interval and you get minus this set. And this is why, for us, this will be enough. Okay? Otherwise, it will be something. So, you have something which I would call Theorem X, Theorem X. This is the statement, which is if Sm minus 1, so this is the length of the interval in which you are. If Sm minus 1 is less than 2m minus 3, then S plus T, Gesundheit, is at least Sm minus 1 plus m. You see, the size of the set plus m, if this is short. And if it is large, this is Theorem 11. If not, well, if not, you have to be careful because then you go into something which is arithmetic progression. You see, if you have something which is at most 1/2, the GCD of the element, the size of the arithmetic progression is obvious 1, because if it is larger than 2, then you must have more than so many elements. So this will go into the business. So you assume that the GCD, I make some comment about that, of S1, S2, blah, 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 up to Tm minus 1. You can put 0 also if you wish in the GCD. You have at least one element which is not 0 and it means something. But if the GCD is equal to 1, well, you see, say that the GCD is equal to 1 is just to say that this is in an arithmetic progression with it's not in an arithmetic progression with a difference which is larger than 1. You see, when you are saying arithmetic progression, if you assume that 0 is in your set, then just to say what is the common multiple of all your elements. This would be the difference of the arithmetic progression. So you heard statement given with arithmetic progression. This is exactly the same thing to speak about the GCD as soon as you have 0 in it. Another way also in the general case is to take the GCD of all the pairwise differences. Okay, so if the GCD is equal to 1 and, of course that is important now, Sm minus 1, you treat the other case here, is at least 2m minus 2, then S plus T is larger than 3m minus 3. This is the 3k minus 3 theorem. Yes, so one sequence will be in what we are doing. We'll get it already with one sequence. But in general, you have this. For our case, you may also assume that this is for one sequence. It is 1. But the real statement is with 2. So better to keep it in mind because this will make all the business will be enough. Okay, so I think I explained you about the philosophy behind. So we can go now to our business and forget about that anymore. Okay. So let us go into the business. So I take A, be a Semfree set. I mean the statement has been given already here of 1n. Okay, and with a, oh, well, I don't know if I have to repeat it, but okay. With capital A, I repeat, is larger than 5 over 12 m plus 2. Okay, this is what we are doing. And now we want to squeeze something and to get something about the structure of that. Okay, so what we do is to consider the difference, A minus A. Okay, so if we took the difference, which is A minus A, then we will have positive elements and negative elements. So this will be, it is a symmetric set. This set is symmetric with respect to 0. So what you have is something which will be A minus A plus union A minus A minus union 0. I think it, okay, take you some time, but I think the notation is clear. Those are the positive, strictly positive elements in A minus A. Those are the negative element, and this is 0. And so it is disjoint, okay? Okay, and then you have something that if you are looking at the cardinality of A minus A, this is 2 times the cardinality of A minus A plus 1. Okay? Let us call that equality 1. Okay, there is, up to now, there is nothing. Usually it is like that up to the end of the proof. Except that if we want to create the proof, it's something different. Now we know that A is Semfree. So this is interesting because this set is also in 1n. You are taking the difference of 2 elements which are between 1n. It is between minus n and n. You don't have the set 0 and you don't have the negative sets. And so all these elements are in 1n too. Okay? So since you know that A is Semfree, you have the following that A plus A minus A plus, those two sets are dependent, and you can say that you go up to capital M, by the way, this will be the same thing. No point to consider larger elements. Okay. So this is just to express the fact. We express, you see, to get n over 2, we're just expressing that, except that in this set, we're just taking the element n, capital N minus something, capital M minus something. Here we are taking all the differences. So we are a bit more, so possibly we are going to get something better. Okay, so now what about the GCD of the elements of A? Okay, the GCD of the elements of A so I take A minus the little m of A. So assume that GCD is what I want to prove in some way, that the GCD is 1, so that I am in good position. Yes? No? Sorry? For 2, yes. What I say is that if you take this element, you see, assume that you have some common element in A. I write it here and I will erase, okay? So assume that you have something that A intersection A first that this is empty. This is empty because your set A is a set which is Sumfree. Okay? This is just to say that it is Sumfree, it is difference free, and so you have this. Now, of course, you may take something which is a subsequence of this one. If you take a subsequence of this one, this is also empty. But this is included in 1n, and this on 1m, if you wish, and this is also included in 1m. Okay? So you have two sets which are in the same interval 1m and which are disjoint. So the sum of their cardinality is at most m. No, thank you very much. You better ask for something instead of going on, because those arguments are not very difficult, but if you miss it, you may spend then half an hour to understand why, and then you say, haha, it is trivial. It reminds me of the story of Littlewood. And Littlewood was giving a course, and at some point he said, and this is trivial. And then he stops, and doesn't find immediately what it is. You know, in that time in England, you had some little room close to the lecture hall. So he goes to the lecture hall, and he comes out of the lecture hall a quarter of an hour later, and he says, yes, it is trivial, and he goes on. So this is the type of triviality. If you don't see it, you can spend a lot of time. So, okay. So the GCD, assume that the GCD, I don't know if I have to write everything, okay. So we consider this. Let us say I call it G is equal to the GCD of that, okay? If G is larger than 3, what happens? Well, you have elements in the set 1M which are in an arithmetic progression of difference 3. Then you have something which will tell you that cardinality of A is less than, forget about the big O of 1, you see in all these things, but this is at most m over 3. Okay? And if it is at most m over 3, it cannot be this amount. Good. If G is equal to 2, then since you have 0 in it, if the GCD is equal to 0, you don't care whether you have 0 or not, because m of A, you don't know whether m of A is even or odd. You have no information about that, about the minimum of A. But you don't care. If the GCD of all these elements is 2, then it means that either all of them are even, all of them are odd. if all the elements are odd, then you are happy. I mean, you are happy, you know that you cannot say anything because you know that if you have any set of odd numbers, it's fine, it is Sumfree and there is nothing much to say. There is no other structure than to say that it is just odd numbers. So, okay, so all elements are odd. All elements of A are, I mean, if I say either odd or even, it may be a curious statement, but I don't say each element. I say all elements. I hope it makes sense that all are even, all are odd. If all are odd, you don't care. Assume that all are even. Well, if all are even, then you can consider, so if all elements, so then let us say that with our inceptions, all elements of A, since there is one even number, all elements of A are even. Okay? So you can consider the element A over 2, 1/2 of A. By the way, 1/2 of A, I mean the A over 2 when A belongs to A. Okay? Well, this is a Semfree set. Yeah, but this is, if this is a Semfree set, it is a Semfree set, is Semfree set in 1 M over 2. It makes sense. M over 2 is an integer here, but you don't care about that. Okay, so there are all that. But if you have a Semfree set here, you have at most M over 4 elements. Okay, then you have cardinality of A is at most M over 4. You see? Okay, boom, tilt. Doesn't work. So G is not equal to 2, so you are sure now that G is equal to 1. So G is equal to 1. I'm almost tempted to erase that, if it's fine with you, okay, to say that the GCD of all the elements is equal to 1. All the element of this GCD is equal to 1. Okay, so I am just concentrating the argument and to say G is equal to 1, it is obvious. Good. Okay. So now we consider two sets. Let S be the set A minus M and T, which is equal to N to M minus A. You are used to that, to say you have a set and you use the plus. If you have, more or less, you should write something that this is the set A minus a set with one element, but you are used to, write it like that. I think it's fine. So you see what we are doing. Maybe I put some little drawing here. So I have something which will be my set A. A is something between N and M. Those two elements are in A. Okay, this is the minimum, this is the maximum. So what I am doing in S, in M, is what I am doing is that I just change the numbering, and this is M minus M, and this is my set S. Okay? Just shift by M. The other one, I just do the difference. So I start here with the 0, and blah, 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 I go to M minus M. In some way, this one I read in this sense, and this one I read in this sense, with the same set A, the elements from A. Okay? Good. So now I am in a good shape, because S is something which has a certain number of elements. This will be, little m will be cardinality of M. Is the set you have. The set T is fine too. It starts with 0. It goes to the same value. The same value, S of M will be capital M minus little m. We are happy also with that. And if needed, the GCD of all the elements, and you are right, here it is enough to have it for one part of it for the S elements. The GCD is equal to 1, it is what we proved. Okay, so we're in a good shape now to discuss about ready to apply the extended in some way 3k minus 3 Frerman theorem. Okay, so we're happy with that. And blah, 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 blah. Everything is fine. Okay, we can shift. Now there are two situations. First situation, first case, m minus m is larger than 2 cardinality of A minus 2. This is just a case. I don't assume that this is true. I want to check how it goes when this is true and how it goes when this is true. So this is exactly the Theorem 11 we are going to use. Okay? We are saying exactly that Sm minus 1, this is m minus m, capital M minus little m, is, no, is larger, sorry, yeah, it is Theorem 11. M minus little m is larger than 2, m is capital A minus 2. So this is exactly Theorem 11 now. Okay? So, what Theorem 11 implies? Theorem 11 implies that A minus A, well, of course, then you see what it is, that if you are taking, looking at the number of elements in A minus A, you will get something which is exactly S minus T, or S plus T, because it is just a shifted set. A minus A, let us write in general, A minus A is a shifted set of S plus T. So A minus A, this is S plus T, is larger than M minus little m plus cardinality of A. Of course, you have also cardinality of S is equal to cardinality of A, cardinality of S is equal to cardinality of S is equal to cardinality of A. Okay? So this is just the difference, the size of this set, plus the number of elements. Good. Okay, and now you build on that and you work a bit. Sorry?
This is from Theorem A.
Yes, you are right. Yes. What did I do? Possibly I started with the yes, you are right. I am in this case, and this case is indeed Theorem 11, and so I don't have this. Thank you very much. I was too quick in that. So this is 3k minus 3, so this is 3a minus 3. Thank you. Okay. Okay, and so you know something about A minus A plus. A minus A plus will be this time larger than 3A over 2 minus 2. Okay. And then this implies, little calculation, this implies that M of A, M, is, you know that it is larger than A plus the number of elements here. So since you have a lower bound for this, you have a lower bound for capital M, and you have m which is larger than 5a over 2 minus 2. Okay? And then it means something that it is larger than 25m over 24. Maybe you forget about the big O of 1, there is something to be a bit more delicate, simply because you know something that A is larger than 512 over m plus 2, okay? So when you have something which is 5a over 2 minus 2, maybe up to big O of 1 or something like that, but then you are happy because it tells you something about the size of m, and the size of m, you get a contradiction that, what is the contradiction? That m is something which is larger than 1 point something m, okay? This is much larger than 1m, okay? So this is fine. So you are happy with that, and so this is done. So first case, you may forget about it. This is not possible. Okay, it's not possible, it's done, we have everything. Maybe I don't erase it right now because it will be a bit complicated. I erase this. You have the picture that essentially SNT are really good people for using Frerman theorem. So, okay, second case, you don't have that many cases here. The second case is that m minus m is at most 2a minus 2, or is less than 2a minus 2. Good. And since this is less than 2m minus 2, or is at most 2a minus 3, you can write it like that if you wish. Here you have just integers, so there is no problem. It works well to write it this way. Okay? And now you can apply Theorem 10. Okay, what Theorem 10 tells you? That Theorem 10 tells you that a minus a plus a minus a. Remember that a minus a is the same thing as a shifted set of s plus t. So the number of elements is the same thing as a cardinality of s plus t. And so m minus a this time is larger than the size of the set in which they are plus the number of elements. Okay? The sum of the set where they are is m minus m, and plus cardinality of A, which is the cardinality of S or the cardinality of the A, or whatever you wish. Okay, so this tells you already something, and again, you use relation 1, you use this time, this one, and it tells you something, of course, on A plus A. So it tells you something that A minus A plus is larger than 1/2 of all this business. 1/2 of m minus m plus cardinality of A minus 1. Okay. So, okay, now you have to work a bit, starting from our hypothesis on capital A. Okay, yeah. Oh, yeah, I have to hurry a bit. But I think this is just inequalities, the same kind of inequalities we had this, that will tell you something that from that you get something that m, maybe I write it once more, m is larger than 1/2 of m yes, this is how, plus 1/2 of m minus 1/2 of little m, and plus capital A over 2 minus 1/2. Okay, this is just what you get from this. using the fact, using always this relation, okay? So you get that, and again, it tells you something about 1/2 of m is larger than, maybe I squeeze some little things, and you will get something that this is larger. You see that it tells you something about m using the fact that you know something about cardinality of A. You are saying larger that. Why is it true? Why is it true? I'm saying, no, I am saying something stupid. Let me go back slowly, I think. This is not true. This should be cardinality of A. There is a cardinality of A, because in 1, you have this, and here you have cardinality of A. In 2, you have cardinality of A, here, and M. So it is cardinality of A plus 1/2 of M, minus 1/2 of little m, plus A over 2, and so on. Okay, this seems to be good. Maybe I have now, since I am hesitating, better to write this so that you can see whether it makes sense. Minus m over 2 minus 1/2. Okay, this is just to concentrate the thing, and this is larger than, you see that A is larger than something in M. So you forget that, you put M somewhere here, and you get something which is 15 over 24. This is fine, the 15 over 24, because you are multiplying 5 over 12 by 3 over 2. So this makes sense, times M. And then you have something which is minus 1/2, which is 12 over 24m, okay? And then you have still this constant, you don't care much. And what you get is that, what I say 1 over 2, no, it's 1 over 2m. It's not m, it's not 1 over, yeah, it's 1 over 2m, is larger, and this is larger than m over 8 minus 1/2. 3, yeah, minus 1/2. Okay, 15 over 24 minus 12 over 24 is 3 over 24, which is 1 over 8. And it tells you that m is essentially, little m is larger than 1/4 of m. Okay, so it is a first result which tells you that m is larger than capital M over 4. Maybe minus some little junk or something like that. Possibly you don't care much about the little junk. Don't know why this has disappeared in my business. Why did this disappear? I don't know. Okay. So this is 4. So possibly now this is something I can erase, which was to say the first case does not exist, so we are always in the second case. So I can erase that. In some way I tried to keep, you see, what is useful under the eye. But, this is, by the way, why I much prefer to give a talk with a board than to give a talk with slides. The information you can keep in front of your eyes is very much limited with slides. Okay, so it is not second case, it is we have. I agree that the first case was, yeah? Sorry? Minus 1, yeah, minus 1, okay. Yeah, it may be that something has to be tuned as regard the big O of 1. I don't care. Yeah, okay, this is larger than that. And so possibly what I wrote is that little m is strictly larger than m over 4, which may be exactly, which has been tuned according to the different values of m mod 4, but at the very end everything is working. But you see, in this statement depends really on the result of the m mod 4, so don't pay too much attention to that. Okay. So now we have already, you see, we have already got some information. Now we're going to build on using this information and to try to go one step further. Because what we want to get is something which is better than m over 4. We want to say that m is larger than a. Okay? Well, we have done a little step. It's good. So, okay, now we consider A1. Okay, let A1, and this again, you have really to check what is the value of MA, because this is not exactly correct what I wrote here, but I don't want to change it on the board. It will be just losing time for really. So, now I have something which is 1 m over 4, no, m over 2, and A2 is A intersection m over 2 plus 1. Usually this works, but not always, so, and m. So you see the point is fine because A1 is something of interest for us. Because A1 is exactly this one. And we want to say something about M1, the size of A1. So this is of interest for us. Good. So, okay, now what is interesting is that A2 is included in m minus 2 little m plus 1 and capital M. This definitely is somewhere where some little tuning has to be done. But roughly speaking, you know what it is. M is larger than m over 4. So 2m is larger than m over 2. And so this set is larger than this one. Okay? So you have something which is definitely larger. Good. Well, this is fine. Now, the point of interest here is that this set, you can write it as the union of two sets. This is the union of two sets which have shifted by little m. So this is the set m minus 2m plus 1, m minus m, union m minus m plus 1, capital M. So you have two sets which are shifted by little m, but little m is an element in A. So the number of elements on A you may have is, at each time you have an element of A here, the little m plus is not in this one. If it is in this one, then the other one is not. So indeed what you have is that A2 now, the cardinality of A2 is included in this set. But it is also a subset of A. So the cardinality of A2 is at most little m. You see that, do you understand? This is a set of length 2m. Okay? So what I can do is consider the first part and the second part, and they're shifted by little m, which is an element of A. So the number of elements in A you have in this set is at most little m. Aha, good. Is it fine? Yeah, we have A2 is at most little m. Okay? Now, what we have is also the following. Okay, this is fine, I can erase that to say that in this case, essentially I have this inequality. This is why I used the 3k minus 3 Frerman theorem, or the compact case of it. By the way, the two cases are quite different. One is just very easy to prove. The compact one is easy to prove. The Theorem 10 is easy to prove. Theorem 11 is more, you already see that it is something like the 3k minus 3, and so it is not as easy. Okay, so now what you have is the following, that A2 is less than that, but now if you look at 2A1, by 2A1, let me write A1 plus A1 so that there is no, so A1 plus A1. A1 plus A1, intersection A2 is empty. Bar was not at the right place. Simply because A is Semfree and so it is difference free. Okay. No, it is Semfree. Don't say more. Now, what can you say about 2A1? Well, 2A1, I mean A1 plus A1, better to write it like that, because 2A1 may be ambiguous. The way I was writing, one half of A was the half of the elements of A, so A1 plus A1. Now, if A1 is inside this interval, well, of course, A1 is indeed, let me recall just one thing. A1 is included, now, of course, it is in M over 2. By definition, there are no smaller elements. I say I take all the small element, but all the small element I could have said directly from here that it is included here. I take only the small elements, okay, so it is included in that. And you know something, that M is larger than M over 4. And so this is included in M over 4 minus 1. And this is the minus 1, which is not in my notes, so I may soon say something which is a bit crazy, but okay. M over 2, so this is a 1, and so if you take M over 2, and so if you take 2A1, A1 plus A1, A1 plus A1 is included in M over 2, and when you add this together, you have at least M over 2 minus 2 and something which is M. Okay? And so the cardinality of 2A1, so 2A, cardinality, what I'm writing junk, but okay, I know that A1 plus A1 intersection A2. Well, what is interesting is that A1 plus A1 is also in the same interval. I should have been more careful about that, but okay. Up to big O of 1 terms. But I mean, the big O of 1 is 1, 2, or 3, and you have really to be more cautious that I was in my notes. Yes?
Don't worry.
No, if you have something to say, it's surely interesting.
No, I'm just not sure the statement of the theorem. Maybe it's 2m minus 3 instead of 2. Then you get 2m minus 4. I'm not sure.
Here? Oh, no, you see, if you have something like 2m, 2m is something which is trivial. If you add two terms, two sets with okay, if you add two, No, I mean, it's important because, you mean here, 2m minus 4, or at the result?
No, 2m minus 3 instead of 2m minus 4, and 2m minus 2 instead of 2m minus 3.
Here you said 2 minus 2 would be also good. Or you mean here?
No, never mind. I meant 2m minus 2 should be 2m minus 2.
Here. Okay. Yes, but I put equality and equality, so there is no other choice. If I say it is strictly larger than, if I say that it is strictly larger than 2m minus 3, it means that it is larger than or equal to m minus 2. This is the opposite. But you think even this doesn't work?
No, never mind.
Okay, what you think is that let us take the same,
No matter whether it's stated correctly.
okay. In any case, you agree if it is up to big O of 1?
Yes.
Okay. So, okay, I agree, there might be constant to tune, but no, but I am pretty sure of this one. I'm pretty sure of this statement, but I am less sure of what I am writing here about this, but in some way you get the philosophy and the fact that the constant we get are, I mean, okay. So, A1 plus A2 is this, and so where are we now? Okay, A1 plus A2 is A, and we have something which is, so cardinality of, I wrote something curious here, but okay, so this is the cardinality of, so now, cardinality of A is cardinality of A1 plus cardinality of A is plus cardinality what I'm saying now. Up, let me 1 second. Oh, yeah, okay. So I have also something that cardinality of A1 plus A1, I have a lower bound for this. The trivial lower bound, if you double some element, you get at least 2 times the number of element minus 1. Okay? And I have no idea about the structure of A1, don't care much, but in any case, this works always. By the way, this result is, oh yeah, I gave you some example yesterday to show that this was in some way the best possible you could do. Okay, this is larger than 2 times A1 minus 1. Okay, so you get something which is 2 times A is what? 2 times A is at most, so this is larger than 2 times A minus 1, so it means that this is 2 times A1 2 times A is at most 2 times A. Yes, so 2 times A is at most 2 times A1 plus 2 times A2. This is equal. I am lost. Let me 1 second. I think it's 5. A2 is less. We have to use this now. 2 is less than M. A1 is less than M over 2. So I have sorry? So I have an upper bound for A. Yeah, so 2A is, yeah, I have upper bound. So this is equal to 2A1 plus 2A2. This is just the definition of A1 and A2, and I multiply by 2, so this is fine. And 2A1 is at most A1 plus A1, and A1 plus A1, which will be at most, from here, it is at most M over 2 m plus 1 over 2 plus, no, here it is 1/2 of, why I have 1/2? A1 is from here. So it is 2 times something like m over 4. Okay, plus constant. Let me stop with that, otherwise I'm really too lost now. 2a is 2a1 plus 2a2. So 2a1 is here. So this is something like m over 4. Okay? So it is something like 2 times m over 4. And a2 is at most m plus m. Okay? In any case, you see the constant you have, you may play with the constant here. So maybe you need to put something which is a bit larger than 2 and then you recover everything. Okay? So this is not really too bad. Fine. And on the other hand, you have this is at most something like you use that a is larger than what you have at the beginning. So this is less than 5 over 2, so it is 5m. No, what I'm saying. Did it make sense? We have this? No, A is larger than, this means nothing. A plus A? Yes.
Know the cardinality. The cardinality has to be at most the length of the interval minus the elements of it. Because A1 plus A1 cannot intersect A.
This is enough? Okay, let us go on. This is less than, so m is at most 5 over 12 times m, and here I get 5 over 24 times m. So this is fine. This is what I want. Oh, yeah, yes. No, I think it's fine. It's fine. So, okay, this is larger than just we use what we have. So it is 5 over 6. 5 over 6, it's enough, it's what I want. 5 over 6 times m plus something which is 2 here, so it is 4. Okay? This is just using that. And so this is 5 over 6, and this is 1 over 2. Okay? So it tells me something that finally m, little m, is larger than something. This is 1 over 2, I can put it 1/2, I can put it here. Okay? And so it tells me that it implies that m is larger than m over 3 plus 2. So check with this number, and this number is not good. change the number here, and you get something which is good. Okay. It's fine. Okay. Oh, no, sorry, I prefer to finish that because otherwise it's really a mess. It's already a mess, by the way, but it would be a bigger mess. Well, we're close to the end. Okay. So now this is the next step we have, is to say that M is even larger than what we had. And so what we get is that A is included in M, capital M, this is clear. And so it is something which is included in itself in the interval M minus 2M plus 1, capital M. So this is fine. And we know already, we have done the proof that this element contains at most little m element. Okay? So the cardinality is at most little m. We proved that already. You see, saying that it can be the union of two elements which are shifted and so on. So this gives you something that capital A, M of A, is larger than cardinality of A, which was the first statement we had, that little m has to be at least cardinality of A. Okay? This is the way we prove that what are the only sets for which we have the cardinality is exactly n over 2. Okay, this is fine. So this is the first inequality, and the second one is not too difficult. So, okay, again, we have to show that, I say show that because it's not difficult to observe, but I cannot write everything. M minus A1 plus A1, A1 plus A1, and A2 are pairwise disjunct, are pairwise disjoint subsets of M over 2 plus 1 M. Okay? So, of course, this is also the, okay, they are all like that. And so you have just to work a bit on that. And now you have M minus A is also included. So M minus A1 is included in 0 M minus M. Okay, A1 plus A1 is included in 2M capital M. All elements, you are just summing elements which are between M, and you know that the sum by definition of A1 is at most M. So this set is here, and M minus M, we know already that M minus M also is at most 2M. This is something we proved here, that M is at most, yeah, this is the point here. Okay? Good. And A1, you know that it is in this set M, capital M over 2. So now, since they are pairwise disjunct, we get the following. Let me do it here. Okay, since they are pairwise disjunct, we have the following, that M cardinality of M minus A1 plus A1 plus A1 plus A2 well, they are all in this interval with at most m element. So this is at most capital M over 2 plus 1 or m plus 1 over 2, something like that. And so we have, and using also this relation, we have the following, that this is 2A1 plus A1. We get the following, that 3A1 plus A2 plus minus 1 is less than m plus 1 over 2. A2 comes from here. A1 comes from this one, m minus A1, because m minus A1 in this, so you have at most capital M minus little m. And the little m disappeared, and this gives you something that A1 is at most m over 4 minus A over 2 plus 3 over 4. And this is to tell you that you don't have many elements which are smaller than m over 2, which was the second inequality in the conclusion of Frerman's theorem. Okay? So I think it's this constant should be good, but you have to tune it a bit. But to understand the general feature, you may forget about this little constant. Okay. So okay. Well, thank you. We'll do something different.